Hi, guys. Let me just keep admitting people into the meeting here.
Okay.
Give it another minute to let people arrive, and then we'll start. Okay, I think I'll start off with some administrative stuff really quick before so I can kind of let people arrive in. So as we've been emailing, I've been getting emails from people over the weekend about postponing our test, and so it looks like we're in a good consensus about it. That instead of having our test this Thursday, we're going to have our test on Monday. Okay. What I'd like to do, since we're going to have our test on Monday, I've been trying to think about how we're going to do that, because we've usually started our tests on Thursday afternoon, and then you guys have had the 24 hours around that. So what I think we'll do is, since we're not going to have the test this Thursday, we'll finish up chapter 7 today. If you guys have had a chance to see the video, if you haven't, you'll have a chance to take a look at it over the weekend. Stuff that we're going to talk about today, I'll kind of mention stuff from the video, but it's not necessarily required that you would have needed to have seen the video in order to be able to follow along with stuff today. But the video will cover the t distribution. I'll talk about that in a minute. Then we'll finish up chapter 7 today. Tomorrow, I'm looking at the syllabus. Tomorrow we'll do chapter 9.2. Okay. So it'll be Wednesday. And then I think on Thursday, we'll swap basically our days, Thursday and Monday. So on Thursday, I'll cover chapter 9.3, or at least start it anyway. And then, so make sure you guys have downloaded the lecture examples page from there, and I'll make sure that you have all needed tables and stuff up online for that as well. So Thursday we'll cover 9.3, but 9.3 will not be on the test. The test will include up to 9.2. Okay, so the test will be, it looks like maybe chapter 5.3 to 9.2. And then 9.3, which we'll do Thursday, that's kind of getting a head start. And then on Monday, what we'll do is maybe I'll start the test at our class time at 10 o'clock in the morning, or I can start it, so I can start the test at on Monday at 10, and then basically go until Tuesday at 10, a 24-hour window around it. We can try to iron out the details about how that's going to work. So anyway, so we can think about how we're going to do that. But the 9.3, I'd like to basically start that on Thursday, so that we can swap put our tests on Monday instead of on Thursday. You know, let me know if you have a problem with that. And then I think we'll still have time to do 9.4 and 9.5 next week, and then have a day or so of review to be able to go over these things, to be able to talk about stuff for the final exam. I've been talking with the course coordinator and the other instructors for the final exam. And what it looks like, maybe what we're going to do is, for the final exam, is instead of it being a cumulative final, we're going to maybe have it on perhaps just the second half of the class, or maybe even just on like the latter half of the material. We'll kind of, you know, pick and choose. I think some other instructors are going to do things from like chapter 5 onwards instead of for the whole semester like we would normally do in a normal semester. We're kind of in extraordinary circumstances here. And then we may even change the weighting of the final, maybe count it as another exam, and kind of boost, like basically make all the exams, you know, including this, you know, final exam as one of the exams. We're still kind of ironing out the details, but I'll let you know as soon as it gets ironed out. Normally we have this all ironed out before the semester even begins, but because we're in extraordinary circumstances, some stuff is administrative stuff is still in flux. So I thank you for your patience on how these things are kind of work out. We're trying to be as considerate of you guys as possible, because we know that you're, you know, at home instead of in a classroom, you know, taking these tests and things. So anyway, like I said, as soon as I know about the final, I'll let you guys know in terms of things. But I think it's going to be, I'm looking at the calendar, I think it's scheduled for either Monday or Tuesday of that week, which is the 22nd or 23rd of June. It's most likely, I think what we'll do is maybe have a 24-hour window around that as well. So I can start it like maybe Monday afternoon at 4, and then it'll go till Tuesday afternoon at 4. That way we can account for, you know, time zone changes and other final exams that you may be trying to juggle. You know, like I said, I think you guys probably should have told me about your conflict finals maybe at the beginning of the semester, but if you've got some kind of conflict, please let me know right away so that we can figure out a way to work around it. But I think with the 24-hour window, it kind of handles a lot of conflicts with the final exams. So I think that should be about it for administrative stuff in terms of our schedule. Okay. So just to recap, okay, our test is gonna go from 5.3 to, let's see, 5.3 to 9.2, okay? And then remember, we'll take homework again. Why not take the homework on Monday, which is normally, like we would have taken it on Thursday, but I'll give you guys, you know, because of we had off yesterday, I'll give you guys some extra time to finish the homework and then to study for the exam. So I'll take the homework due on Monday. Let's see if I can remember to change it. I think the Blackboard is set up to allow you to submit that, even though it'll be quote late. So I'm not going to worry so much about that part because I don't penalize you for handing in things late. And then also I noticed too, I was going back over, some of you have submitted old homeworks like for the points back. I was going back over gradebook and then regrading them and then changing the grade. And then I would put in the new grade on the gradebook, and then, but I would notice that it didn't update the grade on the gradebook list. Okay, so if you have resubmitted old homework, if you can go back just to check to make sure that the grade on gradebook for your resubmitted homework is accurate, like open it up, take a look, see what the score is, right? So if you've got like, if you went from a 5 to a 10, say for example, it should say 10 in the gradebook. If it doesn't, if it still says 5, pop me an email. Okay, so I can go in and check it, because I think when I tried to make these changes over the weekend, gradebook wasn't updating it, or it wasn't updating it very quickly, even though it was in there, but like the listing didn't say, you know, 10, it still said 5. So if you have resubmitted old stuff, just go back and check it just to make sure that the grades are what they say that they are on the graded, you know, homework stuff. And then I can go and change it manually. It should have changed it, but you know, whatever. Okay, so administrative stuff. If you have any questions, send me an email and I'll be happy to clarify. All right, so a couple things. Let's make sure we're all on the same page about tables that we are going to need, because I put up a bunch of stuff on Blackboard this weekend and over the last day or so about tables that you guys are going to need. So we have been using, I'm going to show this. This is our Z table that we've been using so far. Okay, so Z table we use when we know our population standard deviation. Okay, or if the number of samples is really big. Like, so if we're way over, like if we're close, like way over 100 samples, you know, that we've gathered in our sample set, then we can assume that basically we're dealing with essentially a population. Okay, one of the things that we talked about in the video is how do we know if I should use a t-test or a z-test? Okay, and I'm just gonna, you know, do a quick review of this. So you use a z-test, okay, when you know your population standard deviation, okay, if your n, all right, is less than 30, right, my sample size is less than 30, but you were told that the data is normal and you know the population standard deviation or variance, then you can use your z-test, okay? If the population size, if your sample size is less than 30 and you're not quite sure if it's normal or not, if you haven't been told, you need to use a t-test, okay? Or most importantly, if you do not know the population standard deviation, which is going to be the most likely case, right? So in reality, you've got some hypothesis about things. People out there maybe done some of the research. They've come up with conjectures about what the population mean and variance are doing. You have your own, right? You're going to gather your own set of data. You have your sample mean and you have your sample variance. Okay, that's basically all the data that you're working with is the sample. You're going to be using the t-test. There are 2 t-test tables up online. I wanted to show you. One is, this one here is a nice one. This is from a different statistics book that I have. I kind of like how they spell things out. They really kind of let you know confidence interval, you know, upper tail probability. Be careful, your t-test is different than your z. This is one of the things we talked about yesterday. On your z-test, right? So z is our critical value. It marks the point at which, right, we're taking this bell-shaped curve and we're looking at the area, right, to the left of this critical point. So if I want a value that's to the right of that critical point, I have to do 1 minus, okay, stuff that's to the left, okay? And also on our Z table, right, the values here are probabilities. These represent areas under our curve. The sidebars here represent our Z values, okay? So we can compare our test statistic and our critical value. our t-test, okay, like I said, this is from a different book, which I like. This one here I photocopied. It says Larson. That's our textbook officially. So you might kind of want to get in, familiar with this one too. This one does degrees of freedom all the way up to 100, right? So our t-test deals with degrees of freedom, which is based on our sample size, and it deals with our alpha level. See, our alpha, this is our probability. It's just we only get 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7 different probabilities. That's it. Whereas on our Z table, right, I had like a whole table. I had like 100 probabilities that I could work with on my Z table. But on my T table, I only get 7 probabilities. And this table is a table of T values, okay? So I've got degrees of freedom, I've got my alpha, okay? And I have my T value that I'm using. And my T, you can tell on my graph, right, that this is the area, right? And it's basically to the right of that marker, T alpha, comma, degrees of freedom, right? And that's my area under that curve, and it's to the right of that, okay? So that's what this represents here. That's my alpha, okay? And then this, right, you can see our degrees of freedom go all the way up to 100. Beyond 100, it says infinity. Now you're on the Z table, okay? So you might as well switch over to the Z table if you want to do it. Also, the other day, I posted a formula sheet on our web page, okay? It's got 2 sides on it. I printed mine out double-sided. The formula sheet's for you to use. It's a great way to make sure that you have all your formulas correctly written down. It's also something when we teach this in class, right? I give out copies of the formula sheet. I give out copies of the T table, the Z table, and I'm going to talk about another table today. These things, now normally students in the in-class class, they get this formula sheet plus one other full sheet that they get to write their own formulas on. But this is a great formula sheet just to make sure, did you write things down right? Are you thinking about things correctly? It kind of talks about stuff. So this is, make sure you've got this, at least that you've taken a look at it, because you want to make sure that you've written things down correctly if you're referencing your notes. Today, we're going to be talking about variances, which is, this also comes from our textbook at the end, table A.3. It looks like my scanner kind of made things really blurry here, but this is what we call a chi-squared distribution, and it's a reference of variances. We're going to talk about that today. So make sure this is a table that should be up online on our Blackboard page. Okay, chi-squared table. So degrees of freedom, probability here, and we're going to talk about how we read this. Okay, so this is our chi-squared table. Okay, so just some things that you guys want to make sure that you've got up online that you've printed out, maybe that you can use to reference. I know that we've been assuming that our tests and our books, our tests and our quizzes and stuff are open book, open notes. I just don't want you to talk to people, okay, or look things up online or use some kind of like an online, equation solver program. So it kind of opens up for you that you could reference your notes on things, but these formula sheets, the tables, they can really help you to consolidate your ideas. Okay, so that's enough administrative stuff. I'm going to pick up on chapter 7, kind of where we left off from the video. The video before talked all about the T table, okay, and when we would use the T test, okay, and how do we do it? How do we, work through examples? How do we think about it? So today, it's not necessary for you to have watched the video in order to be able to follow along today, because I'm going to start from scratch. We're talking about variances today. But please, have a chance to take a look at that video before, before the weekend or during, obviously before the test, so that you know how to do things. Okay. Okay. So with that said, make sure that you've got your lecture note example sheet printed out for chapters. It's 7.2, 7.3, 7.4. They're all grouped together because I think 7.2 is just kind of like a really short chapter where they say, kind of words like introducing things. 7.3 and 7.4 kind of, blend together in terms of topics and stuff. So we've kind of just lumped them all together into one big chapter section. All right. Also note too that your homework for this stuff is only on chapter 7.4. That's not a mistake, just the homework problems from 7.4. Okay. So with that said, I'm going to start 7.2, 7.3, 7.4. And this is continued. Okay, so what we're going to talk about today is a test for variances, and like, why do we want to do that? Okay, so so far what we've been talking about is checking our mean values, like our t-test and our z-test are looking at like we've looked at its normal distribution, and we've looked at where's our mean, where's our sample mean, where's our true mean, where's our sample mean, you know, where's our population mean, where's our sample mean, you know, how are the means comparing to each other? Okay, so if we write that down, if we say, so if we look at, say, a selection of random samples from, we'll call it a normal distribution. We're going to assume all the stuff that we're doing is normally distributed, unless otherwise stated. Right. We usually look at the mean, right? Because it tells us like sort of the big picture about like what's happening between these populations, right? And this is the mean is going to show us the effect of the experiment. Right. I change one parameter and I check the effect of the experiment. That's when I look at the mean, right? My mean value stuff. Okay, but maybe I want to take a look at the variance, right? So looking at right, which is our sigma squared measure. I'm looking at the variance is going to measure the precision of the experiment. Remember way back in the beginning of maybe chapter 5 or something, or chapter 4, when we were talking about our normal distribution curves, right? So here's our mean, right? And then we say this is with a particular sigma value. So that this has sigma, we'll call the sigma equals 1, right? So then if I have a higher variance, right, I'm going to get the same kind of, you know, my peak will still be at the same spot, but let's say this is sigma equals 2, okay? So my variance is higher, right, on this, so that my curve is spread out. Now, what I like when I take a look at experiments, I like a really nice, well-defined bell-shaped curve. Okay, so I want my variance to be as small as possible on my random samples, right? Because it's going to tell me that whatever I'm measuring is pretty precise. It's actually looking at the variance on our statistics. When you do research, you're going to take a look at, you've gathered all the samples, you're going to take a look at the variance even within a particular patient or subject, or within a particular sample, like you want to do multiple repetitions, say, for example. Then when you take a look at that, if the variance on there is really high, say one subject, you bring in one person to measure, you know, the perception on something, and they're giving you widely variable responses, like, so their own answers are not like around some, you know, you expect them to have a small variability, but if their answers are like all over the map, maybe they're not paying attention, or they're just somehow not a reliable subject. Taking a look at the variance is going to give you justification for maybe tossing out that piece of data, okay, because the subject matter, the person themselves aren't very reliable. Okay, so taking a look at the variance is going to help us look at the precision. As a whole, right, as a whole population, if I look at the variance, if the variance is really wide, you know, maybe I need to do some reevaluations on what I'm testing for or how I'm conducting the experiment. Okay, so variance is really important. All right, chi-squared. So let's talk about it. So an unbiased estimator for our variance based on its maximum likelihood estimate. Remember, we call this the MLE, the sample variance. Okay, so our sample variance S squared 1 over n minus 1. So this gets rid of our bias, right? N minus 1, I equals 1 to n. Okay, so we need to be able to take a look here to get rid of our bias, right? So then if I want to take a look at the ratio of my population to my sample, and I want to get rid of the bias, okay, this right here, our ratio, n minus 1 times our sample variance all over our population variance, right? So we're comparing our sample to our population variance. Now this right here would be our hypothesis. Say, for example, this is based on the data that we've gathered, okay? So this comes from like 1 over sigma squared. Right. So this here has a what we call a chi-squared. Chi is our Greek letter, chi-squared distribution. Okay, this is chi-squared distribution. We say it has n-1 degrees of freedom. Okay, so we need to use a chi-squared table in order to help us make some decisions about this. Okay, so I'll draw out what that is, but we usually reference our chi-squared. We say, I'm gonna go chi-squared, right? This has some probability value, which we'll talk about in a minute, and it has a degree of freedom. Okay, so that we get a chi-squared value. We say chi-squared based on some probability, comma, df, degrees of freedom. Okay, I'm gonna draw a picture in just a minute. You guys tell me if you need more time to finish writing it down before I flip the page.
Just
a sec. Okay, let me know.
okay, thank you.
Great. Okay, so I'm going to flip the page here. So we're going to draw some chi-squared pictures, and then we're going to take a look at our table. So we're going to use our chi-squared table, which is table 8.3 in our book, right? This is what it looks like. It says, right, lower, upper and lower percentiles of chi-squared distribution. Can't read it very well in this scan here. Chi-squared distribution of with degrees, df, degrees of freedom. Okay, so that's the table you want to be taking a look at. Chi-squared table for making inferences about our variance, our population variance. So just like we did with our z table and our t table for making inferences about our mean, right? We're going to use our chi-squared table to make inferences about the variance of our experiment. Okay, so let's write down some stuff. So n is our sample size. S squared is our sample variance, right? And sigma squared, okay, is our population variance. Right, this is the thing that's typically unknown, our population variance, right? But we have a hypothesis about it. So it's the basis for our hypothesis. This is our observed data, right? I've gathered out all these samples. I've gathered n samples. They have a variance of s squared, okay? I think my population has a variance of sigma squared, but I'm going to use my chi-squared table to talk about my confidence in that. So let's just write out what this looks like. Okay, so if I have a degree of freedom equal to 1, my chi-squared table is very peaky. So this is a degree of freedom equals to 1. Okay, it's pretty unusual. It doesn't, inspire a lot of confidence if you've only got like 2 samples that you're working with. If I've got a degree of freedom equal to 4, and then degree of freedom equal to 9, and then again, like if I've got something like say 12. Again, like anything, the more samples that you have, right, the better, higher confidence you can have in things because you have a higher degree of freedom. It's just basically kind of irons things out in terms of even the variability, right? So like you understand about when we go out and we do a poll, if I poll 2 people, I'm not going to be able to make a whole lot of inferences about the general population based on these 2 people. But if I polled like 2,000 people or 20,000 people, you can see how the power of my statistic is much more. Okay. So let's talk about some properties before we get into our examples. Properties of the chi-squared distribution. Okay, so this is coming from, we're looking at table 8.3. Okay, so like a lot of our distributions, all our chi-squared values are positive. I mean, they could be 0, but basically it's mostly asymptotic right out to our x-axis here. Okay, but essentially they're positive. The chi-squared distribution is a family of curves that are based on degrees of freedom. You can see that right here. I kind of drew out some of the family members, right? So my degree of freedom for 1, they share a same basic shape, right? You know, they're kind of generally shaped like this with like sort of this long tail on the right-hand side, okay? And the bump over here on the left-hand side, okay? But they all share the same basic shape, and it's basically dictated by how many degrees of freedom we have, okay? The area under each chi-squared distribution is equal to 1. Okay. Also, our chi-squared distributions are what we call positively skewed. Right? That means I get the bump at the beginning and then a long right-hand tail, right? So even though I'm kind of flattening it out in terms of degrees of freedom, I still see the bump here at the beginning, and then I still get this long tail that goes out on the right-hand side. Okay, so that's what it means to be positively skewed, as opposed to our normal distribution, which is symmetric about the mean. Okay, the chi-squared is all the activity at the beginning, and then it flattens out at the end. Okay, so let's just talk about what this kind of looks like. All right, so I've got this as a chi-squared. So now area equals 0.05. I want to draw out just an example, and that corresponds to a chi-squared value of 1.145. We're gonna practice how we read our table and how we do things. I just want to kind of show you what things look like just a little bit. The area here equals 0.01. This is all for degree of freedom equals to 5, by the way. And this chi-squared value here is 15.086. Okay, so don't sweat if, like, what am I doing here? We're going to actually work through a lot of examples. By the end of today's class, it'll become clear. How do we read the table? How do we think about our tests of variance on here? Okay. So because of our asymmetry, right, this isn't like our normal curve where it's a nice bell-shaped curve. We have an asymmetry. The chi-squared tables need to provide cutoffs for both left-hand tails and right-hand tail. Okay, so right, I've got this cutoff for my left-hand tail. I've got the cutoff for my right-hand tail. We're going to talk about how we're going to calculate it, because if you look at our chi-squared table, I only have this here, so it's only giving me the left-hand part. We're supposed to calculate the rest of it. We're going to work it through, so don't sweat it. So let me just write down how that looks differently in our book. Some books are going to give you like both the left and the right. I think, let's see, the other one, other chi-squared table that no, I think, yeah, I have another book. I have different statistics books. Some books will give you both the right and the left. Our book only gives you the left-hand portion. So our book gives you stuff like this. So they're going to give you a chi-squared value that's based on P. We're going to talk about what P is in just a sec. P, and based on degree of freedom. This here is our area equals 1 minus P. This is equal to our alpha value. It's all going to become clear as we work it through. But just to note, some tables, some books will give you both the left and the right hand chi-squared values, because we need both left and right, because it's asymmetric. And then, but our book only gives us our right hand value. So we have to be able to work with this part. But we're going to teach you how to do that. All right. So give you guys a second to finish writing that down. And then I'm taking out my lecture note example sheet. we're gonna work through the first, couple examples. Example 7, A, B, and C are all about how do I read the table and how do I think about things for right-tailed, left-tailed, two-tailed tests for getting chi-squared values. So does anybody need more time writing this down here?
1 sec.
Okay, let me know when you're ready. Was that great? Okay, so this is our lecture examples. Example 7a, find the critical chi-squared value. So like remember how we did with our t-table and our z-table, we had to calculate our critical value so we can compare it with our test statistic. We're going to do the same thing with our chi-squared. So to find the critical chi-squared value for degrees of freedom 15 and alpha 0.05, and we're told that the test is right-tailed. So I'm just going to draw a quick picture so I can visualize. It's going to look something like this. So if it's a right-tailed test, right, I'm looking at what's this chi-squared value. Okay, so my degrees of freedom is 15, right? So I need to come up with my probability, which I'll do in just a second. And I've got 15 as a degree of freedom. And now this right here, it's going to mark off, okay, the area. This right here is my alpha, 0.05, which is equal to 1 minus p. Okay, I mentioned that 1 minus p because on our chi-squared table, these letters, these numbers here correspond to p, which is alpha equals 1 minus p. So I have to do a little bit of math before I can read the table. And then I'm going to look up my degrees of freedom on the side. Okay, so they told me that the degree of freedom equals 15. So that's going to help me read through this column here. I'm going to go on to my degrees of freedom equals 15 column. But first I have to calculate what the p is. So p is 1 minus alpha. Okay, so if I plug in my alpha, so p equals 1 minus 0.05. So my p-value is going to be equal to 0.95. Okay, so what I do is, right, given my p is equal to 0.95 and my degree of freedom equals 15, I scroll down and I'm going to go here and here. So I'm looking at a chi-squared value of 24.996 is how I'm reading the table. So then my chi-squared, 0.95. So my chi-squared of 0.9515 equals 24.996. That's right here. These first several examples are, how do we read this table anyway for right-tailed, left-tailed, and two-tailed tests? Okay, so that's for a right-tailed test. Okay, so I have to translate this into a p-value. Okay, just a little bit. So we're told the test is left-tailed, alpha is 0.05, chi-squared value 10 degrees of freedom. Okay, so let's just, I'm going to draw a quick picture again. I'm going to draw these the same basic shape. Okay, so I've got my chi-squared. It's a left-tailed test, so I'm looking here. So I'm looking for chi-squared, okay, and my degrees of freedom is 10, okay, and I'm going to calculate out stuff in a minute. So this here is my area, okay. This here, because it's left-tailed, that's just equal to my alpha, which is 0.05. Okay, if it's right-tailed, okay, it's alpha equals 1 minus p. If it's left-tailed, right, I'm just using the alpha. That's the area under this curve is 0.05. Okay, so I've got 0.05, comma 10 is how I'm going to be reading this table, right? So I look at, so I'm going to go chi-squared 0.05, 10. So I'm going to look up here. So 10, and then 0.05, 3.94 is my chi-squared value. Okay, so this is 3.94. So just so you know, look, the chi-squared values get bigger, right, as I move out across on the x-axis, right? So on my left-tailed, my chi-squared value was almost 25. When I'm on my on my right-tailed test, my chi-squared value was almost 25. On my left-tailed test, my chi-squared value is almost 4. Right? So you would expect that in terms of our values. Okay, so just kind of keep that in mind. The big thing is that the area equals alpha on a left-tailed. The area equals basically 1 minus alpha. Okay, on a right-tailed. Okay, so we're reading our table. Let's scroll up a little bit. Part C says we have a two-tailed test. We have 22 degrees of freedom and alpha equals 0.05, and we're looking for our chi-squared value. Let's draw that out. We have a two-tailed test. Exaggerate the asymmetry here. So that means I've got something here and then something here, okay, that I've got to take into account. I'm looking for these cutoffs. This is going to be my chi-squared value, my chi-squared on my left, my chi-squared on my right. So this is our chi-squared left, chi-squared right. Okay, I have to calculate out, figure what those are. So it's two-tailed, right? So I have to do something with my alpha. So I have to go alpha over 2. Right, so it's going to be 0.05 over 2 is 0.025. Okay, so that's the first part. So now what happens is I'm going to break this up into left side and right side. Right, because remember on our left side it's purely alpha. On our right side I have to calculate the p-value. So on the left side this is just simply alpha, alpha over 2, right, which is equal to 0.025, and my degrees of freedom equals 22. So I look it up on the graph, on my table. So I look up and go, I'm at 22 and 0.025, so here. Okay. So this is chi-squared left, which is equal to 10.982. Okay. 10.982. On my right-hand side, okay, I have to do my p is equal to 1 minus alpha over 2. Okay. So this is 1 minus 0.025. So my p-value is 0.975. Okay. My degrees of freedom is the same, 22. So I'm looking at the chi-squared on my right-hand side. Okay. So I'm looking at degrees of freedom 22, p 0.975. So I go, here's 22.975, and I cruise down, and I'm right here. Okay. And that's right here. So this is 36.781. So we would write this as chi-squared 0.025, 22. This is chi-squared 0.975, 22. Okay, chi-squared is always written as our area, right, our alpha or our p-value essentially, and then comma degrees of freedom. Okay. So that's how we're reading the table. Okay. Give you guys a second to finish writing that. And I'm going to make a note about our hypothesis testing. Okay, when we're doing a hypothesis about the variance, what is that going to look like? So we'll put that down and then we'll start working on our examples. Okay. Anybody need more time to finish writing down what I've got here? Okay. All right. So if we're doing hypothesis testing with chi-squared, we need to think about right-tailed, left-tailed, and two-tailed. So on my right-tailed, my right-tailed test is going to look like my null hypothesis. My sigma squared, my variance, equals to some value. I don't know what that value is. Some number, some value. Okay, versus our alternative hypothesis, which is the chi-squared is greater than some value. That's the same value, right? So this is just like we did with our hypothesis testing on our mean, only look, I'm using my variance. My variance is going to equal some value. My right-tailed test says that my hypothesis is that it's actually greater than that value. Okay, greater than. And all these things are defined in the problem that we're reading. The researcher thinks that the number is actually greater than. That's going to tell you it's a right-tailed test. Left-tailed test. Okay, let's write down what our hypothesis is going to look like. Right, we've got our null hypothesis. Our variance equals some value. Oops, some value. Versus our alternative hypothesis. You guys can imagine if it's left-tailed, right? We think it's going to be less than that same value. Okay, and that comes from the nature of the problem. I've got some, population information. I've gathered my own data, and my hypothesis is that, actually the variance is less than whatever this value is. And I get this value, based on doing the reading, based on looking at what other research people have been doing, what else is out there in the world. Okay, two-tailed test, right? Remember, you can kind of see where this is going, right? So our variance equals some value versus our alternative hypothesis is that the variance doesn't equal that value. So it's really similar to the stuff that we did with our mean, right? Only now we're working with our variance, okay? And because we're working with the variance, we need to be able to look at our chi-squared test to check the variability, okay? Right-tailed, left-tailed, two-tailed test. It's all going to depend on how the problem is worded, or for you, when you're actually out in the real world, what kind of experimental question you're working with, or what are you asking? Do you think things are going to be? Okay, great. So I've got my lecture examples, and I've got example 8. We're going to pull out. We're going to start working through.
How do we calculate our test statistic for chi-square?
Great. We're going to do that. It comes from, what did I do with my notes here? Our test statistic actually is right here. It comes from this ratio here. This is the basis for our test statistic, this thing right here. But I'll put it into the examples, right, so that you can exactly see. But this is your test statistic for chi-squared. I didn't actually make that very clear, but I'll write that down in our examples. Okay. So example 8, right? So a psychologist wishes to see if the variance in IQ of 10 of her patients is less than the variance of the population, which is 225. So this is our population variance, okay? So the variance in IQs of her 10 patients, this is our sample variance, was 206. We're going to test the claim at the alpha level 0.05, okay? So let's do what we have been doing so far, state our hypothesis, our critical value test statistic, and all that. Okay, so the first thing we're going to say, our hypothesis. Okay, so our hypothesis is that our variance is equal to population, 225. Our alternative hypothesis is that our variance is less than 225. This is our claim. This is what the psychologist thinks, right? So this is going to be, it's less than, which means it's going to be a left-tailed test, okay? So when we calculate out our critical value, right, it's less than is what we expect. So we're looking at a critical value on the left side. Okay, so this here is our alpha, which is the area under the curve from this chi-squared point, okay, that we're going to be calculating. We're going to be looking for this, looking this up in the table. Then we're going to calculate our test statistic and compare them. So our critical value, this is a left-tailed test. Okay, so now our degrees of freedom. Okay, she's got 10 patients, right? So the degrees of freedom is n-1, so our degrees of freedom is equal to 9. Okay, so our alpha equals 0.05. My degrees of freedom equals 9. I'm going to use that on my table. Right, I'm going to look up degrees of freedom 9, my alpha 0.05, and I'm going to find my appropriate chi-squared value. That's my critical value. So this is, that comes from my table. Okay. All right, now the test statistic. Okay, which I'll put a box around the formula so that you can be clear. So I'll write that in, put the box in. So the test statistic that we're looking for, a chi-squared, okay, n-1, so our degrees of freedom times the sample variance divided by what our hypothesized population variance is. So we're going to plug things in. We're going to calculate out this chi-squared, and we're going to compare it to our critical value. Let's plug things in. So this is going to be 10-1, our sample variance. Now don't square 206, because they said the variance of her 10 patients was 206. So I'm just going to put 206 here. That's my variance already. Don't square it. Your numbers will be off. Okay, the population variance was 225. You know, I'm going to multiply, divide everything out. So I'm going to find a test statistic, my chi-squared test statistic as 8.24. Okay, so my test statistic, so this is my critical value. My test statistic is here. Okay. I'm going to see where our decision is going to end up. The decision, so I'm going to write it out. I have to justify it. Our test statistic, which is 8.24, was greater than our critical value, which was 3.325, okay? Which means my decision is don't reject. Not reject the null hypothesis, okay, which means we don't have enough evidence to support the claim that her patients have a smaller variability, okay?
This is fail to reject the null hypothesis.
Yep, fail to reject. Yep. Don't reject, fail to reject. Don't do it. We don't say we accept the null hypothesis, we just say we're not going to reject it. We don't have enough evidence to reject it. You don't have to write this part, not enough evidence to support. You don't have to write that part in your answer. You just have to write what your conclusion is, right? We're not going to reject the null hypothesis because here, like, you need to justify it, right? So what you're doing is you're showing in all these different steps, right? You're showing you understand what the hypothesis is. You'll have to state it. What's the hypothesis? What's the test statistic? What's the critical value? And then what? I have to know that I have to compare the test statistic and the critical value. And based on the fact that the test statistic, right, is outside of my critical region, it's greater than my critical value, right? I'm not going to reject the null hypothesis. I don't have enough evidence to be able to do that, okay? This is what you need. You don't have to write this part. This is just so for you, like, you know, like what it is that we're actually saying here when we say we're not going to reject the null hypothesis, okay? Anybody need more time to keep writing? Okay, so let's go into the next example. We're basically working through examples. Okay, so example 9 says, a hospital administrator believes that the standard deviation, now be careful, look, we're tricking you. The standard deviation of the number of people using outpatient surgery per day is greater than 8. A random sample of 15 days, that's our N, is selected at alpha equals 0.10. Can we support the claim? Assume that the data is normal. Okay, so they think is greater than. So when they're using words, right? So we're going to start parsing through and decoding the question that's being asked. So this is sigma, okay, when they're and their sample, okay, our sample standard deviation and our population standard deviation. Remember, our chi-squared is a test of variance. So if you're given standard deviation, you have to square it, okay, so that you can actually use the chi-squared test. If you don't square it, your numbers are going to be off. Okay, so we're given that and we're told that it's greater than, which is going to tell us that we're using a test that's going to be right-tailed, right? Because we're talking about a claim that's greater than. Okay, so random sample of 15 days. So let's work it through. So we're given the data, which means that from the data, you'll have to, I calculated it for you, I'll give it to you. From the data, you would have to calculate, ultimately you'd have to calculate your mean and your variance, right? And to compare these things. But from the data here, our variance is equal to 11.2 squared, right? So the standard deviation of our data is equal to 11.2, okay, of this data here. All right, so now, right, because this is, I'm sorry, this is not, that's, okay. So let's go ahead and write it down. So our hypothesis, based on what we're being told here, our null hypothesis is that our variance is equal to 8 squared. Okay, I'm writing this out specifically like 8 squared so that you know I'm taking the standard deviation and I'm squaring it. Okay, so be careful. You can write 64 if you want to. I'm just letting you know that we have to make that calculation. Versus our alternative.
How do you know, like, what part of the problem is telling us that we need to use chi-squared?
They said standard deviation, right? So standard deviation and variance are related by square root, right? So if they're giving me the standard deviation and they're saying they think that the basically standard deviation and variance are telling us the nature of the variability of the data, right? So I've got my normal distribution curve. So if I've got like a really small standard deviation, my curve's going to be fairly peaky. If I've got a really wide standard deviation, my curve's going to be fairly flat, or like flat-ish, like much more rounded, right? And so what they're looking at here, they're not measuring the mean anymore, which is before we looked at the curve and we looked at another curve and we said, how far apart are those means, right? And that was going to give us our significance. Now we're looking at essentially, is the variability of the population similar or the same statistically speaking to the variability of our own data? Because if our own data is really variable, right, then maybe I'm going to need to draw some other conclusions about the comparison of the means. I'll have to do something different, right? So remember, we based all of our our tests originally on whether the population variance was known, right? So did I do a z-test or a t-test? So if I can assume that the variability between my sample and the population is the same statistically, right, then I can use a z-test. I'm going to use the population instead of my sample. If the population of variance is statistically different than my sample variance, I'm going to need to use a t-test because I'm going to need to be comparing it with my sample variance. They're different enough, okay? So often what happens in experimentation is you gather a bunch of data, you calculate the mean, you calculate the standard deviation or the variance on your own sample data. Before you do any kind of like Z or T test, you do a test of variance first to see, you know, is my variance of my sample statistically significantly different from the population variance, my assumption, right? And that's going to determine what test I use after that, my Z test or my T test, okay? Because those decisions of what test to use, testing on the mean is going to be predicated on is the population variance known or not? So, but to answer your question, how did I know? Because they told me, right? They said, I think standard deviation, if they said, I think the data is very variable, I think it's, you know, whatever. So we're not even, like, we didn't say that the mean number of people is 8. We said that the variance basically of the amount of surgeries per day is this, right? So that's, we're kind of reading the question and that's, it's giving us a clue whether we're dealing with a chi-squared or with a Z or a T test. Does that answer your question?
Yeah. So basically,
Kind of,
we weren't given the mean, so we know that we need to use chi-squared.
it's not just that we weren't given the mean, even if we were given the mean, but they said, is the standard deviation greater than the population standard deviation, right? So the question, the nature of the question itself says, we're comparing our standard deviations, right? So even if they had given us all the information, but they asked us just about the standard deviation, that tells us we're doing a test only of the variability. We're not checking the means at this point. Okay.
Okay.
Yeah. So what test to use and how to use it should be specified in the problem itself, right? So we got clues like the word greater than. It's going to tell me it's a right-tailed test. Let me finish writing this down. Sigma squared is greater than 8 squared. This is our claim, right? So that here comes from this word here. Like if they said, is it different than, I'm going to do a two-tailed test, right? But they're telling you about to check the variability of these things. I want to compare my sample variability with the population variability. Somewhere out there, somebody's done a study where they said, oh yeah, you know, the variance is like blah, is like 8. Well, you know, based on my data, is the variance, you know, greater than that? Maybe our hospital has a much higher degree of variability than the general population. That's like what they're kind of thinking about. But it tells you within the problem itself. Okay, so we stated our hypothesis. Let's talk about our critical value. So our critical value, right, comes from our table. So this is a right-tailed test. Right, that comes from here. So right-tailed test, I'm going to draw this out like this and try to exaggerate the asymmetry of it. So this is my area. This is my chi-squared value that I'm looking for. That's my critical chi-squared value. They said alpha of 0.10. So that means this area here, okay, is equal to 0.10, which is 1 minus p. Remember, the p-value on the right-tailed test is the thing that I need to solve for, that I have to look at, okay? But the chi-squared test based on my degrees of freedom, okay? So my n is equal to 15, so my degree of freedom, 15 minus 1, 14, right? N minus 1. Okay, so I looked this up on the, first I have to calculate alpha equals 1 minus p. So 0.1, 1 minus p. So my p-value is equal to 0.90. So I look up on my table degrees of freedom 14, my p-value of 0.90. 0.9 and 14, I'm looking things up, and I find my chi-squared critical value as 21.064. Okay, that's based on the criteria that they gave me at the alpha 0.10 level and degrees of freedom. This defines our critical region. This is what I'm going to be comparing my test statistic to. Okay, so our test statistic. So we calculated our variance from the data offline. So we have our S squared already. So remember the test statistic, chi squared equals n minus 1. Our sample variance all over our population variance. This is our hypothesis. This is our data. Okay, so this is going to be n minus 1. This comes from 11.2 squared, right? My population is 8 squared. Okay. So I plugged all these things in. Be careful, they gave us standard deviation, so I have to square it in order to get the right value. So my test statistic chi squared after plugging it all in is 27.4. Okay, so that, right, if this is 21 and the values are increasing, my 27.44 is right there. Okay, so I'm well within my critical region, right? So I'm going to use that to help me make my decision. Okay, so let's write down why. So we're going to talk about test statistic critical value comparison. So my test statistic, which is 27.44, is greater than our critical value, which we calculated at 21.064. Okay, therefore, you can reject our null hypothesis, okay, because we're falling within our critical region. Okay, we can say that the standard deviation or variance at this hospital, standard deviation at this hospital is greater than 8, based on the evidence that we have here. Okay. So we're using our chi-squared to talk about the variability of our data versus some population value. Okay. That's good. And up the page. Okay, example 10. All right, a cigarette manufacturer wants to test the claim that the variance of nicotine contained in its cigarettes is 0.644. We're going to assume the data has a normal distribution. Random sample of 20 cigarettes has a standard deviation of 1. At the alpha 0.05, is there enough evidence to reject the manufacturer's claim? Okay, so they're not saying anything about we think it's greater than, we think it's less than, right? We're just saying, is it different than this? Okay, something being different than means we're talking about a two-tailed test, right? So let's talk about our hypothesis. Right, so our hypothesis, our null hypothesis, is that our variance is equal to 0.644. They gave that to us here, right? Versus our alternative hypothesis, sigma squared does not equal 0.644. Okay, it's two-tailed, right? Because they didn't say, we think it's greater than, we think it's less than. If they don't specify, you can assume that it's going to be two-tailed. It's not equal to. Okay, so this is our claim here. Just writing that down for you. You don't have to write that down. Let's talk about our critical values now. We've got 2 because it's two-tailed. Okay, so this is a two-tailed. So I'm just going to draw out a picture. Helps me visualize. So I've got some kind of asymmetry, right? And then I'm going to have something here, and then I'm going to have something here. Okay, so I need my chi-squared on the left and my chi-squared on the right. Okay, so it's a two-tailed test. Because it's two-tailed, I have to split my alpha into 2 pieces. So my alpha equals 0.05. My alpha over 2 is 0.025. That's this region here. Alpha over 2, 0.025. That area under the curve. This area here, okay, is going to equal to, also has to sum up to be 0.025, but we calculate this in terms of a p-value, okay? So I need to calculate my p-value. We'll keep that in mind when we come back to it with our right tail and our left tail. Our degrees of freedom, they did 20 cigarettes, right? So our degrees of freedom is equal to 19, okay? So we've got my alpha, my 1 minus alpha, my degrees of freedom here. 1 minus alpha equals 0.975. So my left-tailed chi-squared, okay? So this is alpha equals 0.025, okay? Degrees of freedom 19. My chi-squared on the left, which is equal to 8.907, right? I looked that up on my table for degrees of freedom equals 19.025, and I calculated it out. So this is 8.907, right there. That's a 9. Okay, so this is chi-squared 0.02519. My right-tailed, okay, I need to do a p-value. P-value is 1 minus alpha, 0.975. Okay, my chi-squared on the right, I looked that up for degrees of freedom 19. My p is equal to 0.975. This is coming up to be 32.852. 32.852. Right, I just, so 18.975, and I found it. Okay. All right, critical values. This one and this one from our table. Okay, now we need to calculate our test statistic and see if it falls within one of these critical ranges, right? Or does it fall within the non-critical? So our test statistic. Okay, so my chi-squared n minus 1 sigma s squared over sigma squared. So I'm going to plug things in. So my n minus 1, this is 20 minus 1, right? Our degrees of freedom. Our sample standard deviation, right? They gave it in terms of standard deviation, so be careful. All over 0.644. Okay, so be careful. So they said two things. They're trying to trick us in this problem. The variance, population variance is 0.644. A random sample has a standard deviation of 1. When I square 1, it's not going to change it, but you have to be very careful. So this gave me standard deviation. This gave me variance, right? So I square my sample standard deviation, but I leave my population variance as is because it's already squared. Okay, so I multiply, and divide 29.5 equal to my chi-squared test statistic. So I need to take a look. So my 29.5 going to fall right here. So 29.5, say for example, falls right there. Okay, so based on where it's falling, we have an idea about what kind of decision we're going to make. Okay, so our decision, so let's write down y. So I'm going to write my test statistic. 29.5 is greater than my critical value on my left-hand side, which is 8.907. And it's less than my right-hand side critical value, 32.852, right? So it falls within our non-critical region, okay? So therefore, I'm going to fail to reject our null hypothesis. There's just not enough data. Okay, so let's write that down in words. Not enough evidence to reject the claim that the variance of the cigarettes is 0.644. Okay. We need more data if we want to be able to reject it. Okay. Or we need more data to say we're still not going to reject it. Okay. But either way, whatever we have right now isn't enough to reject our null hypothesis. Okay. Anybody need another minute to keep writing on that?
Hold on one sec.
Let me know when you're ready.
Okay.
Okay, great. All right. So we've often talked about like the p-value methods. We're going to do a p-value method with our chi-squared, just to show you how it's done. All right, so example 11 says, a researcher knows from past studies that the standard deviation of the time it takes to inspect a car is 16.8 minutes. A random sample of 24 cars is selected and inspected. The standard deviation is 12.5 minutes. At alpha 0.05, can it be concluded that the standard deviation has changed? And we're going to use the p-value method. We're also going to assume it's normal distribution. We're telling you, like we will on like a test or you know, a final exam or something, we're going to say specifically use the p-value method. We want to know that you know how to do it. Remember, it's just two sides of the same coin. Okay, but we're going to learn how to do that with our chi-squared test. Okay, so let's write down all of our pieces like we have been. So our hypothesis. Okay, so my null hypothesis is that my variance is equal to, watch what they said, standard deviation. So first off, I'm comparing the variances of things, right? So I'm not comparing means of things anymore because they want to know, is the variance, has the standard deviation changed? But my chi-squared test is a test of variance, but they gave me standard deviation, so I have to be careful. So 16.8 squared, okay, I'm going to put that here in my hypothesis, versus my null hypothesis that my variance does not equal to 16.8 squared. Okay, this is my claim here. They didn't say was it greater than or less than, they just said has it changed, which is another way of saying are these things different, right? Which means we're dealing with a two-tailed test. Okay, so now, which makes our p-value method, we have to do an added step, a step at the end. So our test statistic. If we don't calculate critical values on a p-value method, we're comparing our probabilities. Okay, so our test statistic, I'm looking at my chi-squared and -1 s squared all over sigma squared. So I'm going to start plugging things in. So 24 minus 1 s squared. So they gave me the standard deviation 12.5 squared for variance, and then my standard deviation of the population 16.8 squared. Remember, I'm comparing variances. So then my chi-squared is going to be 12.733. This is my test statistic. So be careful. So we're going to need to compare that right with our p-value. So let me scroll this up. So p-value. Now again, with these, anything outside of the z table and our p-value is going to be a range of values, right? Because we're just given our probabilities at the top. Right, and this is a table of chi-squared values. So this is the probabilities at the top. So remember, unlike in our z table where the table is a table of probabilities, now I just have, you know, this sort of discrete set of probabilities at the top, and then I have to give a range of values for my actual p-value. So my p-value, so my degrees of freedom equals 23, right? And looking at the 23 portion, okay, that 23 line on my chi-squared table, my chi-squared of 12.733, this is my test statistic, is going to fall between a p-value of 0.025 and a p-value of 0.05. How did I get that? Let me look again. I'll show you what I mean. So 12.733, I'm looking at degrees of freedom 23. So let's see if I can get this on the same graph. Good. So degrees of freedom 23, right? And I'm looking for 12, right? 12.73. So it's somewhere here in between these two values, right? Between 11.68 and 13.091, right? So I go back up. 11.68 corresponds to a p-value of 0.025. 13.091 corresponds to a p-value of 0.05. Okay, so that's where these numbers come from. Because I don't have an exact number, I just have a range of values. Okay, so but this is a
Is it possible for the p-value to be between like 0.1 and 0.9?
So let's see. So you're talking about a really wide value. So let's say, so if I have a degrees of freedom, let's say of 15, right? So I'm going to go 0.1 is 8.57 and let's say 0.9. Oh, like between here and here. Yeah, right. So then, yeah. So then those are two adjacent. You're always going to be looking at two adjacent values. You should look at two adjacent values. I'm not going to go from 0.1 to 0.99, right? Because my chi-squared is going to fall. This is a pretty wide range, but it just means that I'm basically on that downward slope where things are changing rapidly, right? On my graph here. So this is here to here. You can see how, you know, things on here change fairly rapidly. So yeah, like if I had a chi-squared value of 10, for example, right, and a degrees of freedom of 15, then I would be looking at a p-value of 0.1 and 0.9, right? And it's just, that's kind of just how it's working, and you just have to, you're looking at your table and interpreting it. All right, so I know it seems like a really wide range, but we work with what we have. Okay, so because this is a two-tailed test, right? I can't just compare the p-values with my alpha. I have to do something to my p-value because this is a two-tailed test, right? So I have to double the p-value to get the total area to compare with the alpha. Okay, so remember, it's a two-tailed test, so remember we split things up into two different pieces for one left tail and the right tail. Okay, so now I've got my p-values, I'm going to double them. Okay, so I'm going to say 0.025 times 2, 0.05, and 0.05 times 2 is 0.1. Okay, so these give me my ranges for the p-value. So I'm going to say 0.05 is less than or equal to the p-value, which is less than or equal to 0.1. Okay, that's my p-value. So now to make my decision, I have to compare my alpha to this p-value here. Okay, so I'm going to say my alpha, 0.05, is within the p-value interval right here. So it's really like right on that low end, but we're including it, right? It's close enough that you would actually include it because it's so close. So therefore, because alpha is within that interval, we're not going to reject our null hypothesis. There's just not enough information, not enough evidence to allow us to reject it because our alpha is within this range here. Okay. I want my alpha to be outside of my, I want my p-value to be, you know, in a two-tailed test, I want my p-value to be, you know, well within the critical regions of it. Okay. So that's how you do p-value method for chi-squared. Anybody need more time to keep writing on this?
If the upper bound was 0.05, we would fail to reject it too, because we would
Yeah.
include it in our interval.
Yeah, and I think, you know, you read it sometimes in like research papers where they'll try to argue that because it's right on the bounds, like if your alpha is equal to one of the bounds, they might argue that there's some statistical significance there, that, you know, maybe there's some, they may say that there's enough to warrant like future studies. Like they're going to try to spin it so that things are significantly different. But in reality, mathematically speaking, you know, because it's sitting right on the bounds, we would actually say they're not statistically significantly different. But you'll see it often, like when you read papers, they'll say, you know, the p-value is like right on that bounds. So like it's equal, just about equal to our alpha on one of the ends here, right? So people are going to want to spin their data to make it look like it is actually significantly different. And they may actually just use that as a reason for, say, this warrants future studies, so I need more funding money so that I can go gather more data. And if you gather more data, maybe you will find that it's definitely not significantly different, or it definitely is. So you never know. I mean, with the, this is actually, we have, you know, it's kind of a small, like our degrees of freedom is 23. It's not bad, but it's, you know, the larger the value. Remember our law of large numbers. The more sample sizes that we have, the higher degree of confidence we're going to have in our data set. It's probably a longer answer than you needed, but, you know, in reality, we would say it's right on the bounds. It's not significantly different, but people will claim, you know, that it kind of is because it's right on the bounds.
Okay.
Yeah, sure. All right. So with that, let's talk about confidence intervals with the variance. Okay, so just like we've been doing with confidence intervals for our mean values, right? All of the stuff that we're doing is to say, I'm gathering samples and I want to make inferences about the population, right? I'm gathering samples, I've got their mean values. I want to make inferences about what's the general population doing. So I'm saying 95% confident that my mean is within this range here. Or now we're going to talk about our variance. I'm 95% confident that my variance, right, of the overall population variance is within these two bounds here. So confidence intervals for variance, right? And so we would say, right, we're going to do this our variance, right? So our sample that we're gathering is random, right? So we've got independent samples, right? And we're also going to assume that the population is normally distributed. Okay, there's some basic assumptions that we're going to work with before we start talking about our confidence intervals for variance. So let's set up, right? All of this is to predict, come up with a prediction for my population variance. Right, so my population variance, I'm going to use my chi-squared values. So when we calculated out our chi-squared test statistic, right, if I solve for my sigma squared in that equation, right, I'm basically looking at, I've got n minus 1 s squared all over chi-squared. This is my right-hand chi-squared value. Be careful. Remember, our confidence intervals are inherently two-tailed, right? Because I'm looking at, I've got some kind of, graph, and I'm splitting it up into a right-tailed and a left-tailed portion of it, okay? So my confidence interval around this sigma is going to be inherently two-tailed. So now when I look at, why am I putting the right chi-squared on the left portion? It's because, remember, our right chi-squared values were larger, okay? So when I divide by a larger number, I'm going to get a smaller one. So same thing over here, right? My left-tailed chi-squared values are smaller. So when I divide by a smaller number, I get an overall larger number. So my variance, okay, is going to be between a small number and a larger number, okay? So this is, and this is for degrees of freedom equals n minus 1. Put a box around
Wait, does that say right on the left side?
Yeah, that's what I just said, right? So this says right, this says left.
Sorry,
Why am I
yeah.
I'm putting the right on the left-hand side. Why? Because remember, our chi-squared values over here are bigger than our chi-squared values over here. So if I divide by a large number, right, this is in the denominator. If I divide by a large number, I'm going to get a small number. The chi-squared values on my left-hand side are smaller. When I divide by a smaller number, I'm going to get a larger number. It's counterintuitive. You think it should be on the right-hand side, but it's because this is larger, that's a smaller number, and I need to be able to look at my variance going from a small number to a bigger number. Okay. Okay. So if we want this in terms of population standard deviation, right, I'm just going to take the square root of everything. Okay. So let me just write this down. So s squared equals our sample variance. Sigma squared equals our population variance. So remember, if I want for a standard deviation, right, how am I going to do this? I'm just going to take, I don't have a sigma squared anymore, but I'm going to take the square root of this. You can take the square root of that. So I take the square root of everything to give me my standard deviation measure. Okay. Same thing for my degrees of freedom here. Okay. Do everything all out for variance, and then if you're asked for standard deviation confidence values, then just take the square root of everything at the end. We'll do some examples so you can see. Let me just I'm gonna scroll this up, and I'm going to draw a picture here so you can see. I'm going to try to exaggerate that tail. So chi-squared on our left, oops, let me scroll this up. Chi-squared on our left. This is alpha over 2, that area right here. Let's do this. Chi-squared on our right. And this area here is alpha over 2 here. Okay. So this is 1 minus alpha, this region here. Okay. So we talk about our 95% confidence interval. This is our 95% confidence interval. We split our alpha, right? That's 1 minus alpha gives us our confidence interval. I split our alpha into 2 pieces because it's inherently two-tailed. Okay. This is chi squared alpha over 2, chi squared 1 minus alpha over 2. And we look it up at the table. Degrees of freedom. Degrees of freedom. Okay. On our table, this is our table value that we're looking things up on. Alpha over 2, 1 minus alpha over 2. Okay. When you guys are ready, I'll open up the examples again. Anybody need more time to keep writing?
Hold on 1 sec.
Okay, let me know when you're ready.
Okay.
All right. So I'm looking at our example page, example 12. This is kind of like a quick one. All right, so example 12 says we want to find the chi-squared on the left and the chi-squared on the right for a 90% confidence interval when n equals 25. All right, so let's see. Confidence interval implies two-tailed. So I always like to draw a picture. So I'm dealing with things like this. Okay, so I need my chi-squared on the left, chi-squared on the right. Here's what I'm looking at. And my alpha, did they give, oh, 90, okay, 90%. Okay, so if I've got a 90% confidence interval, we need to translate that into an alpha. So that's going to be 1 minus 0.9 to give us our alpha, which is 0.1. Okay, so then that means that I'm dealing with alpha over 2, 0.05. Okay, so this is alpha over 2, 0.05. That's the area here. The area here is 0.05 as well. But remember, when you look up our chi-squared on the right-hand side, we're doing 1 minus alpha over 2. Okay, so let's be careful. So now, chi-squared on the left, okay, this is our alpha equals 0.05, okay, and my degrees of freedom, I'll write this down, degrees of freedom equals n minus 1, so that's 24. So I'm looking up on the degrees of freedom 24 line for alpha equals 0.05, okay, so I find 13.848. This is 13.848 right there. Okay, that comes from my degree of freedom is 24, okay, and my p-value equals 0.05. I'm reading it from my table. And now my chi-squared on the right. Okay, so this one I have to do a p-value, which is 1 minus alpha, which is equal to 0.95. So that's how I'm reading it over here with the degree of freedom of 24, and I find that's 36.5. Okay, chi-squared left, chi-squared right. Okay, for our confidence interval. Same thing that we did before with our mean. How do I translate my percent confidence into an alpha? Okay, it's two-tailed. I have to do alpha over 2. But now with our chi-squared, we're looking things up either by alpha or by p. Okay. Okay, I'm going to start scrolling up. So example 13 says, large candy manufacturer produces packages and sells packs of candy targeted to weigh 52 grams. Quality control is set up to check that the variability, so this tells us we're dealing with a variance check, variability in each pack is not too great, that some packs weigh a lot more than 52 or a lot less than 52. People would be happy if it weighed a lot more, but the company would probably end up losing money. People would be upset that it weighed a lot less than 52 because they're paying for it, even though the company would make money. In an attempt to estimate the standard deviation, remember this is sigma, standard deviation of our population of all 52-gram packs, okay, this is the standard deviation of that. Quality control takes a random sample of n equals 10, maybe kind of small, but we'll work with it. We're going to check it, right? It's common. They can't check all of the packs that are going out there. They're making like thousands and thousands of packs every day. They can't check them all. So they're just going to just do some random sample. They're going to check it. So this random sample has a variance of 4.2. So we're going to look at a 95% confidence interval from this random sample to estimate our standard deviation. So watch, we're flipping, right, our variables. We're looking at variance, and what we want to estimate our standard deviation. So make sure you're reading the question very carefully so you don't accidentally work with standard deviation when you should have been working with variance and vice versa. Okay, all right, so let's think of what we have. So first off, our degrees of freedom is our n minus 1, so 10 minus 1. So our degrees of freedom is equal to 9. It's going to tell us, we're going to go down to the 9 column and then look things over. So 95% confidence interval means that our alpha is equal to 0.05. Okay, so now I need to do, it's two-tailed, so alpha over 2, 0.025, and I'm going to do 1 minus alpha over 2 for my right tail, my right-hand portion, my left-hand portion is going to be 0.975. So I found my alpha and my p-value. That's going to help me look things up on the table. Okay, so my chi-squared 0.025 and my degrees of freedom of 9, right? I look these up on the table and I find 2.7. This is my left-hand chi-squared value. My chi-squared 0.975, my degrees of freedom 9, right? This is my right-hand side is 19.023. Okay. We were given all this stuff I've just kind of calculated and I looked up from the table. Right. So now we were given the sample variance, which is s squared as 4.2. Okay. And I need to come up with a confidence interval for my population standard deviation. I don't know what the population standard deviation is. I'm coming up with a 95% confidence interval for that. So 95% confidence interval, this sample, confidence interval of our population standard deviation for this sample, or from this sample really. I'm going to say n minus 1 s squared all over chi squared on the right is less than sigma squared n minus 1 s squared chi squared on the left. And I'm going to take the square root of it when I'm all done, after I'm done calculating. Okay, so I'm going to start plugging things in. So this would be 10 minus 1, my s squared, so this is 4.2. They gave it to me as a variance. My chi squared on the right, we were given as 19.023. 10 minus 1, right, 4.2, all over my chi squared on the left, which we calculated, 2.7. Okay, so now I'm coming up with a confidence interval first for the variance, and I'll take the square root of it. So this is going to give me 1.99 is less than sigma squared, which is less than 14. And now for standard deviation, I have to take the square root of everything. So I take the square root of 1.99, 1.41, less than my standard deviation, which is less than 3.74. Okay. So we can say that we're 95% confident. Let's see if I can write that down in a different color. All right, my summary, what this means. 95% confident that the weights of all of the candy packs have a standard deviation between 1.41 and 3.74. Oops. Okay, so we were given the mean, and we can say that the variability in the standard deviation of the weights in these packs is 1.41 and 3.74. Okay, so we took a sample of 10, and we're going to make an inference about the whole population. That's what we're trying to do here, too. It's the variability is between here and here on all of our, I'm sorry, the standard deviation on all of our packs is between 1.41 and 3.74. Okay. You know, if you need more time to keep writing. We have only 2 more examples and then we'll finish up. And I'll scan in this page, this whole lecture example page. It's a lot of pages. So you can take a look at the solutions just to make sure you've written down everything correctly. You guys, do you need any more time? Anybody need any more time to keep writing? Okay. So example 14 says, find the 90% confidence interval for the variance and standard deviation for the number of named storms per year in the Atlantic. To be a named storm means that you've reached some, you know, significance level in terms of your storm destruction capability, right? How fast the storms are and how big. So random sample, they went back 10 years and they found in year 1 we had 10 named storms, year 2 we had 5 named storms, and so on and so forth. Assume the data distribution is normal. Okay, so this is our data for the number of storms per year with n equals 10 years sampled. Okay, so we've got 10 years sampled. This is how many, so we're going to need to come up with our sample standard deviation, our sample variance. Okay, so I'm going to use this data. I did this offline, so you don't have to do it, but you will need to come up with that. In your calculators, actually, you can enter data in a table and then have it do variance and standard deviation. So use the data. Variance of our sample. Okay, so I did that and I found our variance was equal to 16.9. Okay, this is our sample variance. Okay, our degrees of freedom. We have n equals 10, so this is 10 minus 1, so we have 9 degrees of freedom. Right, so we're going to be using that row number 9 to calculate our values. So let's take a look. So 90% confidence, okay, which means that we're dealing with an alpha of 0.1. Okay, it's a confidence interval, so I have to be thinking about alpha over 2. So my alpha over 2, 0.1 divided by 2, 0.05. And then I'm just going to prefetch it. 1 minus alpha over 2 is 0.95. Okay, these are things that I'm going to need for my left tail, my right tail. All right, so on my table, my chi-squared from the left is going to equal to 3.325. This is from the table. Chi-squared on the right is going to equal to 16.919. Okay, so that came from my degrees of freedom and my alpha and my 1 minus alpha, right, from my left and my right. Okay, so I'm going to use that to help me come up with my confidence interval. So I'm going to say n minus 1 s squared all over chi-squared right less than variance, less than n minus 1 s squared on the left. Okay, so we're going to plug things in, our numbers in. Okay, so 10 minus 1 times s squared, we calculated that to be 16.9. Chi-squared on the right, 16.919, less than sigma squared, which is less than 9, 16.9, 3.325. Okay, so now, right, when I calculate these things out, watch out, this is 16.9, so 16.919, so be careful, there's going to be a little bit of bits left over. So this is 8.99 is less than sigma squared, which is less than 45.74. This is our variance. Okay, and then for standard deviation, I'm going to take the square root of it all. So I get 2.99, which is less than sigma, which is less than 6.7. Okay, so what we would say is we're 90% confident a box around both these things here. Confident that the standard deviation for the number of named storms in the Atlantic is between about 3 and 6.76. I'm rounding a little bit in a random sample of 10 years. Putting it into words, you'd only be required to give this as your answer. Okay, but just so you know, like, what does it mean? What are we doing? Okay. One last example, and then we'll finish for the day. Does anybody need more time to keep writing? Okay. So last example, and then we're done. All right, so mutual fund investment. You can take your statistics knowledge and go work for Wall Street or whatever, or some investment house, and then be able to make predictions about how investments and returns are working, and whether the data is actually coming out. How can you make predictions about where things are headed? All right, so in a mutual fund investment, the volatility is measured as the variance or standard deviation as compared to some benchmark, like the take a look at an average number of returns. So we're going to give the investment return percent for 19 years of a particular some fund, right? And we want to find is statistically significantly less than some benchmark. Okay, so I'm going to give you the benchmark. We're going to compare it. We're going to test at the alpha 0.05 level, and we're going to assume that the data are normally distributed. Okay, so this is percent investment return. So these are all 19 data samples. So we would need to calculate things like the variance for that. So given the sample standard deviation of 11.28, so that's our sample standard deviation, so that's S, and our benchmark of true volatility, which is 11.67. Okay, so this is back to hypothesis testing. Okay, so let's write our sample standard deviation, right? So you could enter all this data in and then calculate out your sample standard deviation is 11.28, and it's in percent, so that's where this percent number comes from. Okay, so first let's write our hypothesis. Okay, so our hypothesis is that our variance, 11.67, is our benchmark, right? They gave it to us as standard deviation, so I have to square it, versus our alternative, because our variance is less than, okay, because they want to know, they say it right here, is it less than the benchmark? So that dictates what kind of hypothesis we're testing, which dictates is it right-tailed, left-tailed, or two-tailed. Okay, so our critical value, okay, this is a one-sided test, right? Our left-tailed test. Looks like, I'm not going to try to exaggerate that. We're looking here. Okay, it's our left-tailed test. So this is our alpha. They gave us an alpha 0.05. That's the area under that curve. Here we're going to be looking for this chi-squared value. Okay, so our critical value, alpha equals 0.05. Okay, and then we're doing chi-squared on the left is what we want. Okay, our degrees of freedom equals 19 minus 1, so that's 18. Right, so that's the row that we're going to be looking for on our table. Right, so my chi-squared for 0.05 and 18 degrees of freedom. Right, I looked that up on my table. I find 9.39 from my table. Okay, so that's the thing that I'm going to be comparing it to, 9.39. Scroll up. So 3, our test statistic. Here's where we actually look at our sample data. So remember our chi-squared and minus 1, s squared all over sigma squared. So now I've got my degree of freedom, right? My sigma squared, so it's 11.28. Okay, so that came from, right, we calculated our sample standard deviation, but I have to square it, right, because I'm talking about variance here. And now this is our hypothesis, 11.67. I have to square it to get variance. I was given it in terms of standard deviation. Square everything out, multiply it, divide it, and I find my test statistic was equal to 16.82. Okay, so let's see, 9.39, 16.82. Right there. You can kind of get a feeling for where we're headed in terms of our decision. Okay, so the decision that we're going to make, let's write it out. So our test statistic, 16.82, is greater than our critical value, which we looked up on the table as 9.39, right? So therefore, we're gonna fail, reject our null hypothesis. Okay, so we can say, therefore, based on the evidence that our sample does not have is not statistically significant, does not have from our benchmark. Okay, so we're like close to our benchmark. Statistically speaking, we're not going to reject our null hypothesis. Okay. Chi-squared test. It's an important test. It gets actually used a lot in research because you have to check variability first so that you can know what kind of a test on the means that you should be doing. Okay. All right, and that's it, guys. I'll scan this in, and that's chapter 7. So tomorrow I'll do chapter 9.2. So make sure you have your lecture note examples printed out for that. And then on Thursday, I'll do chapter 9.3. Right, and then on Monday we'll start our test window at we'll start it at 10 o'clock in the morning. We'll go from like 10 o'clock on Monday to 10 o'clock on Tuesday. So it's slightly different than what we would have done, but you'll have the whole weekend. Anyway, I'll have office hours today if you want to come by and ask any questions about homework and stuff. Okay, have a great day.
Thank you. You too.